Every time an autoregressive large language model generates a single token on modern GPU architectures, it hits a hard physical limit. To predict one word, the system must load the entire multi-gigabyte weight matrix across the VRAM bus. This hardware throughput is dictated by the physical bandwidth of that memory connection. Because the data takes so long to arrive, the arithmetic logic units, the compute cores, spend the vast majority of inference time sitting idle, starving for input. Bypassing this traffic jam requires a structural architectural change known as speculative decoding. This draft then verify protocol uses a smaller drafter model to propose a block of tokens. The larger executive model verifies them simultaneously, triggering a single unified read from the weight matrix. This converts the inference pipeline into a compute-dense batch operation. Abandoning sequential memory fetches in favor of parallel block verification extracts the true performance the hardware ALU is capable of delivering. The industry standard approach uses a smaller autoregressive model to draft those tokens, but it still generates text sequentially, inheriting the same memory stall. Discrete masked diffusion offers a highly parallelized alternative, operating on a canvas of categorical token placeholders instead of continuous noise denoising. The canvas rapidly populates with distinct tokens as the diffusion model iteratively refines the entire block simultaneously, locking in correct tokens without causal stalling. Substituting an autoregressive drafter with a masked diffusion engine shifts drafting from a sequential memory problem to a parallelized compute capability, while maintaining terminal exactness. Standard autoregressive generation is forced to wait on sequential memory fetches. In contrast, the diffusion drafter initializes a wide canvas of 256 placeholder tokens at once. The driving mechanism is bidirectional in-block attention. By breaking causal masking, it looks forward and backward simultaneously to resolve token identities, operating entirely within a compute-bound regime to mitigate the bottleneck. Executing a 256-token diffusion block sweep takes a fraction of the time required to sequentially generate those same tokens through an autoregressive model. The diffusion drafter consumes idle ALU capacity to manufacture context, shifting the bottleneck away from the memory bus. Once the fully drafted n-token block is complete, the entire sequence instantly drops directly into the larger autoregressive executive model for processing. The executive then processes the entire block in a single massive matrix multiplication, rather than n separate passes. This uses an exact byte acceptance date protocol. Acceptance is based on deterministic byte-exact ID equality. Diffusion lossiness only impacts efficiency, not output. Any failing token is strictly rejected and instantly overwritten by the executive model's ground truth. The autoregressive executive acts as an impenetrable causal filter, preventing hallucination bleed-through from the probabilistic drafter. When drafts are rejected, standard speculative decoding architectures suffer from memory fragmentation, forcing the system to pause and scrub data. This fragmentation is solved using a quantized KV cache buffer called the Spinor ring. Incoming drafted tokens are written with an uncommitted flag, flipping to 1 once accepted. If a token fails, an order 1 transactional rewind simply decrements the right index backward. Because the pointer just moves, there is no payload scrub and no garbage collection required. This process results in zero memory fragmentation in the KV cache. Treating speculative generation as an atomic transaction ensures the context window remains performant regardless of draft failure rates. During idle computational periods, the system enters the night shift, a deep background execution state dedicated to optimizing memory. Here, the bidirectional infilling engine is repurposed for episodic memory consolidation. The system manages this through the propose gate promote loop. The diffusion engine compresses raw historical tokens, proposing a dense pseudo-token sequence to a temporary shadow ring. The perplexity gate scans this proposal, calculating information loss. Sound compressions are promoted to the permanent ring 3 vault, while lossy results are discarded. Because bidirectional attention allows the model to analyze the entire episode as a single unit, it can identify semantic patterns that causal models miss. It acts as an infilling engine, resynthesizing long spans of history into a single, dense pseudo-token representation. This struct transactional gate secures deep offline episodic compression without risking data corruption. The challenge is executing a 26 billion parameter pipeline on standard consumer hardware. Quantized mixed precision formats are an absolute requirement for deployment. The architecture compresses specific coefficients to 1 byte in Q8, with deeper Q4 reductions applied to specific network layers. This reduction allows the 26 billion parameter architecture to fit inside an 18 gigabyte VRAM constraint. By leveraging discrete integer ALU pipes, this speculative pipeline can operate on setups as restrictive as a 12 gigabyte RTX 2060. We see the masked diffusion drafter, the verifier, and the transactional spinor ring interlocking on a quantized substrate. Replacing sequential generation with parallel diffusion drafting repositions the hardware bottleneck. When the draft accuracy is high, inference speed begins to approach the ceiling of the raw ALU compute power, rather than stalling on the speed of the VRAM.